Yeah. Okay. So yeah, can you? Well, I guess it's already no problem for the people online. So yeah, actually, this is not really my recent work. So this is I will talk based on my. Is it not really working or? Yeah. So this is really based on my previous work with Shan Majid, but because my recent work is more categorical theory, so for geometric audience, I guess it's more interesting to talk about my previous work. So, but basically, I want to talk in this seminar. I will talk about more about differential algebra. So, what is differential algebra? Here, we have a DGA. So let's say we are given an algebra. So K algebra of our field. DGA over A is just the bunch of n form, so direct sum of n form. And where we have the space of zero form is the algebra itself. And satisfying graded Leibniz rule, and d square is zero. And the space of one form is of course the first order differential calculus, satisfying the usual Leibniz rule, who has a surjectivity axiom and so on. And yeah, so that's the DGA, and we call DGA to be an exterior algebra if it is generated by A itself and also by dA or by omega 1. And moreover, in the rest of the talk, I will assume that my DGA to be maximal prolongation of omega 1. It means that in higher degree, in degree 2 or higher, we will not get any new relation. So every relation in my DGA depends on bimodal relation of A and omega 1. Okay. Now, this definition of DGA, of course, it works for any algebra, but we are interested in of algebra or by algebra. So here, if our algebra is half algebra or by algebra, we could have a bicovariant calculus, which is that it means that it has the commuting left and right coactions. And the thing is, Brzezinski proved that if we have a bicovariant calculus, then the whole DGA will become a super bialgebra, or it will be Z2 graded. So here the coproduct, because this is bialgebra, the coproduct on the zero form is the coproduct of the algebra, and the coproduct of the one form will be the left action plus the right coactions. And now we get that's for the coproduct in the higher degree, we can extend it. So like, for example, if we have here eta and omega is in any degree, we can just like calculate it like delta of eta omega is equal to delta eta times delta omega. So let's say if it is, oops, what's happening? Okay. So if this is all degree 1 and degree 1, we got it becomes degree 2, and we got the coproduct on degree 2. So that's one thing. And the other thing is we have a more stronger condition, which is defined by Majid and Tao in 2015. Oh, sorry, yeah. That we have the notion of strongly bicovariant calculus or strongly bicovariant DGA. That it means that our DGA is now a super bialgebra, but also the differential map here is a super coderivative. It means that it satisfies this kind of condition. So basically, this is the graded Leibniz rule. If you dualize the if you dualize the graded Leibniz rule, this is the resulting dual conditions. Okay. Now the problem is, let's say we are given any algebra, there will be many differential calculi on any given algebra. Okay. Okay. And there is a famous construction by Woronowicz. I think this is like the most fundamental one in the works of the differential calculus. It means that so Woronowicz says that any differential calculus is isomorphic to A tensor A plus quotient by some I, where I is the algebraic ideal of A plus. It means that if we want to finding omega 1 or the calculus, we can do that by finding I. But now there's a problem. So usually it's hard to finding I. So basically in geometry, either you are given omega 1, or if not, you have to finding I. But so usually it's hard, especially or maybe at least in the case of cross product by algebra that I want to discuss now. Okay, so I will talk about more specific kind of cross product by algebra, but I want to, before I go to the more detail, I want to remark that the idea of this construction that I will tell you later, it works on any on general construction that considered by Bulaciu, Kanepal, and Torres-Chilas. So what they say that, let's say if we have A and H be an algebra and also coalgebra, but not necessarily by algebra, and then we have like a local braiding between them, two local braiding. This algebra and coalgebra is in monomial category, but this local braiding is not necessarily the braiding in the monomial category.
What does a local braiding mean?
It's just maps like this one with some conditions. The conditions look similar to the braiding in monomial category, but like more conditions. But because it's too technical, I don't think it's just bunch conditions. But it's just happened. The braiding is just local. Local is just this braiding is only for specific A and H. So it's not braiding in the model category. So if we have this two local braiding, then we can construct the cross product algebra or cross product coalgebra. So here, the cross product algebra means just becomes the usual associative algebra. And if our A and H is unital, then they become also unital. And also for coalgebra, similar, but not necessarily by algebra. But then, of course, if we add some more condition, which is, well, the paper of Bulaciu, Kanepal, and Torres-Chilas is full of conditions. So yeah, but basically we can get cross product by algebra as well by adding some more conditions. And the idea is we want to define the differential of the cross product by algebra by the cross product of their differentials. That's the main idea. And to do so is actually pretty straightforward. So to do that, you take the bunch of conditions in the construction of the cross product, and then you generalize it appropriately in the Z2 grading setting, and then basically it becomes super algebra, super coalgebra, and then cross product again because the condition is similar, but just in the Z2 grading, then you got the super algebra and super coalgebra, and super by algebra if you add more conditions. So that's the idea, and it's very general. And because it's very general, in specific case, the construction works in any main type of cross product algebra that usually used in geometry, such as quantum double by Drinfeld, or more general setting of double cross product, or its double cross coproduct by Majid. And what I want to discuss now is specific in the case of byproduct by Radford, and also later by Majid in little bit different settings. But the idea is similar. So let's see what is the idea. So I want to introduce you. Maybe you know about byproduct, but just to remind you. So let's say if we have A to be a half algebra, and B is braided half algebra in the other different category over A. What is the other different module? So B is the other different module. So what is the other different module? It means that B is a comodal algebra and also a module algebra with compatibility between the action and the coaction. Here I denote the action to be delta. I denote the coaction to be delta R and the action to be like, I don't know how to say it, like, yeah, I don't know, but it's just the action like this triangle notation. But it's also, but this heterodifferential category is a braided half algebra. Sorry, it's a braided monomial category. So it means that because it's modular category, we can have a monoid and comonoid in that category. So we have half algebra in the category, and the coproduct, just to differentiate between the coproduct of usual half algebra and the braided half algebra, I denote the coproduct to be underline delta. That's the notation. And because it's braiding, it's still multiplicative, like the delta is still multiplicative, but in the braiding setting. So there is a braiding. So here psi is braiding in the modal category. not local braiding anymore. And if we have such B, we can construct byproduct of algebra. I don't know how to say it, but just byproduct. I don't know what the symbol says, but in English, I mean. But there is a associative product and co-associative coproduct, and this is just usual Hopf algebra, K Hopf algebra over vector space. And it's associative, co-associative, unital. So that's the byproduct. And yep. Psi is the braiding in the monoidal category, the category of vector-driven module. So I will immediately go to the main theorem here, and then I will explain what this theory says. So let's say we have of course, we are given A and B such in this condition. So A Hopf algebra, B is braid Hopf algebra, and then with that additional data, we also have the additional data of omega A to be strongly bicovariant that I explained before, and omega B is also strongly bicovariant. It means it's also how say like strongly bicovariant, but in the monoidal category. Just everything, yeah. And then we can, again, as I said in general stuff, we can define the DGA on the byproduct to be the byproduct of DGA. But now, how we construct the byproduct of DGA? Well, to construct the byproduct of DGA, we need our omega B to be a super Pieter-Drievoort module in the category of module over omega A. So that's the idea. And then if we have omega B to be a super Pieter-Drievoort module over omega A, we have a super byproduct. This is just the same. Basically, this is just the same relation, same product and coproduct as before, but just in the Z2 settings. But now we have the differential on them. So we have differentials, and this differentials is basically looks like the Leibniz rule, if you can see. It looks like the graded Leibniz rule. But now just be careful that here, because this is element of A, this is element of B, then should be differential of A, and here should be differential of B. So that's the main theorem, and maybe I want to explain a little bit more about what does super Pieter-Drievoort module means. It means that, of course, as previous, now we have omega B is a super comodal algebra and also supermodal algebra with compatibility between product and coproducts. So here I have product, and compatibility is actually similar to the ordinary Pieter-Drievoort module, but now just with grading, because everything now is in Z2 grading. And but again, this is in theory it works, but in practice probably not really good, because usually in geometry we are usually given only omega 1 or maybe omega 2, but usually omega 1 and the relational algebra itself. So we want to look what this data means in degree 0 and degree 1. Of course, in degree 0 it means the usual Pieter-Drievoort module, but in degree 1 what does it mean? So the coaction here, so here we have the coaction of A on B. On degree 0, it extends to the coaction on degree 1. So it extends to coaction of A on B to be the coactions of, now it's a little bit getting interested. So we have the coaction to be from the omega 1B to omega 1B tensor A. That's the covariant part. But we have additional terms, which is the B tensor omega 1A. And this is called this is called differentiable coaction by Bex and Majid in their books. And in the explicit setting, let's say if I denote my coaction of B to be B0 tensor B1, my coaction on DB, it just becomes DB0 tensor B1 plus B0 tensor DB1. It's just similar to Leibniz rule again. So, but also we have action and also we need we have coaction and we also need action. The action, yeah, we have A X on B. It's also extends. Maybe I don't really write it like in the space, but in terms of their space. But let's say the extension is just you apply the differential on the whole stuff. So A X on B, and it's also similar. It looks like Leibniz rule again. But maybe it will become a little bit problem later, because if you see in this action stuff, we are just, let's say we are given an action. It's just one action, but then we will need if we want to extend this, we will need two actions here. And this is not obvious. I mean, in practice, in examples later, we will see that this is not obvious how to find this in examples. But in theory, yeah, it behaves like Leibniz rule. But yeah, we will see later in the examples. So I guess, to be honest, that's it. The theory is just it, but just simple. So basically, this work is more calculational. So from this simple theory, we find a bunch of interesting examples, and I will probably compute. Yep. Yeah.
This additional assumption of strongly bicovariant calculus, because like if it's not strongly but just bicovariant, again, take a braided tensor products.
Yeah, actually that's also all right, but because the goal is we want our byproduct of DGA to be also kind of by algebra. So that's why we need kind of coproduct on the differential. Just it. But if we want only consider the algebra relation, to be honest, is but again, in the algebra relation, we will need coproduct here of the DGA. Like, of course, in any DGA, maybe you don't need differential here, but then if we want to look at the maximal prolongation, then probably you will need the coproduct. You will need this conditions. Sorry, you will need the supercoderivation.
I see. Okay.
Because yeah, it's just to make that this behaves like also like by algebra or algebra. So then the goal later the goal is that because this is also by algebra, then any theory in by algebra also holds there. So any theory in by algebra also holds there on the inset grading. But just to have a DGA probably is not necessary unless we are talking about maximal prolongations.
Okay.
I hope that's answers. Okay.
Well, Rita, could you just go back to the strongly bicovariant definition again, please?
Where is it again? Yeah. Okay.
Okay, thanks. Yeah.
Okay, so yeah, this is just the theory for byproduct, and to be honest, for different kind of cross product like double cross product or quantum double, it's basically similar. The idea is similar. So you take their data, about how you construct them, and then just generalize the data to be the Z2 gradings, and then you got it. And the differential will look similar. So let's. So now probably I will talk about more examples if no one has no problem. Maybe yeah. So I will see now. Yeah, I will give a bunch of examples. Simplest one, let's say if your A to be the quantum torus, it's just algebra generated by T with a group like coproduct. And our Breithoff algebra will be the quantum line here. Yeah, probably it should be CQT. I forgot to write Q just to Sorry, CT is unital, yeah. Yeah, CX also unital, so yeah, there is one there. So yeah, here the quantum line is a getter-differential module. The coaction is simple, so because it's just one variable, so the coaction of x is x tensor t, and the action is just that tx on x is q to the power of -2 of x, and the braided coproduct of x is primitive. Well, it's easy to check that it's basically B is getter-differential module over A, and then if we construct the byproduct using the formula and some calculation, and this is the resulting structure. So we have the cross relation between x and t, and the usual coproduct of x becomes skew primitive, and the t is also same. And this is actually isomorphic to the quotient of CKSL2, or one can say this is actually the deformation of Borel subalgebra of SL2. Simple enough, and we want to find the differential structure now. Now, in the theory, maybe I will back a little bit. In the theory here, omega A and omega B is given. So this is probably one of the first interesting observation that in practice, even though in theory omega A and omega B is given, in practice, omega A is not independent of omega B. So omega B is still given. Okay. So for example, in this case, but of course, again, because I want to work on the maximal prolongation, I only consider the bimodal relation between omega 1 and B. So in this case, omega 1b is given by this structure, so the x of x, the x times x is just q squared x dx, and the coproduct of the x is again primitive. Omega now, just by relation on omega 1b, we will find this structure of omega 1a. Okay, and it's because and we got it because we requiring the from this relation, if we apply coaction on them, they should be equal, because yeah, that's the condition, right, for the coaction. And by requiring that their coaction is equal, then we will find the omega 1a. So in what we did in omega 1a, it's just simple. So we did what is dt times t, right? The bimodal relation, we only need that. And then we check that it's satisfied Leibniz rule and so on. And let's see what the calculation, I will just write because it's very simple. So to compute the coaction of the x times x, because it's kind of like algebra, super algebra map, you compute like that. And what is delta r of the x is given there, and then you compute. I don't have laser, but yeah. So basically, for the x tensor t times x tensor t, you have like the x times x tensor t square, no problem there. But in here we have x square tensor dt times t. For the x times x, it's given, so you can write that. But here we don't know, because that's differential of a. We don't know. But for the other side, on the other side, we compute this similar calculation. We got this, and this is just the same, so no problem there. But here, we got x squared tensor t dt. So just by comparing these two terms, we got what is dt times t. And that's it. That's the structure of omega 1a. And then, of course, we can check this is satisfying Leibniz rule and so on. So that's first the omega 1a. And that's the coaction stuff. And for the action, it's a little bit more brute force, because we are given the action of t the action of t on x is usually given. But then we want to find what is the action of t on dx and also dt on x. It's not given, but the only data we know that if we add them together, they should be the differential of dx on x. And it's, well, well, this is a little bit brute force, but I will show you later the more general construction, but maybe so far, maybe maybe you can just take my word on it. It's just, but you can add that, yeah. But yeah, you can extend it to the action on dt on dx, but to be honest, it's not really important because everything is maximal prolongation. And with these actions and the previous coaction, we get that omega 1b is omega b is to be a superior different module over omega a, and then we can construct the byproduct of differentials, and then we got the DGA of the quantum positive Borel-Sue algebra. And this is just the result of calculation. To be honest, it's probably not really interesting, but yeah, it's just the way to find the calculus. Probably the interesting part is the process of finding differential of omega 1a. Maybe you have questions here.
Step back for a second to see what's going on. So you've produced a bicovariant calculus on the quantum Borel of classical dimension.
Sorry, what is?
You've constructed the calculus that you have as of classical dimension.
Yep.
And
no, it's really not really classical.
what is? Sorry, then I don't see what's the problem with the dimension.
No, to be honest, there is not really a problem. I don't see a problem, but it's just.
So what is the dimension of the calculus?
This is just one dimensional thing. But like it's just, yeah, it's just one dimensional. You mean the calculus of A, right? The quantum torus.
No, and the cross product one that you.
The cross product is, it becomes two-dimensional then, I guess. Yeah, because we have px and dt, and
yeah, but then this is of classical dimension.
Yeah.
So, and the calculus is bicovariant by construction.
Yeah.
So you have a bicovariant calculus of classical dimension on the product, which is very good.
Yeah.
And then the maximal prolongation of this, have you calculated the dimension?
Yeah, it's just well, it's just
Well, I guess yes.
Yeah.
From there.
Yeah, it comes from the others. I just don't write it, but well, you can find what is dx dt.
Is it clear from this that then it's you've got omega 1, omega 2, and that's it?
Yeah.
It's clear.
Yeah. After omega 2, it's clear. I just don't write omega 2. Maybe I should write it, but yeah, I just don't. But yeah, there is omega 2 here. You can just apply that.
And then how does this relate? So if you have the three-dimensional Baranovich calculus, is there some obvious relation between these or not?
Not really. I don't know. Not really.
Okay, yeah.
Probably there is, but yeah, I just don't consider it there. But that's the simplest example. And how much time do I have? Quite a lot. Okay. More complicated examples before I go to the more general construction. So if A is quantum coordinate of GL2, so what is this? What is CQGL2 here? Maybe you know this is just generated by ABCD with some quantum relation like BA equal QAB and so on. And also we have the determinant here, and this is also I don't write it here, but D is group like, so delta capital D is capital D tensor capital D. And this is a group like, means that if I have the coproduct of this matrix is matrix tensor matrix. So delta A is, we can just write it like A tensor A plus B tensor C. It just looks like matrix. So that's our A. Our B will be the two-dimensional quantum plane. I read relation. So YX is QXY. It's Bredin-Hopf algebra. So we can. So B is actually a Yatardin-Ford module over A. The coproduct of A on B is given like this, and the coproduct, the action of A on B is also given. This is standard. So in any, I think in many of algebra books, it's given as standard. But B is Bredin-Hopf algebra. So the Bredin coproduct here for X and Y are primitives. And if we just in the degree 0, so this is just in the algebra level, their byproduct, if we apply the byproduct, we will have the cross relation between X and Y and also the ABCD generators of CKGL2. Maybe it's look a little bit uglier, but yeah, there is it's a little bit uglier, but yeah, it just does it. And the co-product is also given. Yeah.
What is lambda here?
Lambda is Q minus Q inverse.
Okay, thank you.
Yeah, so this is really quite ugly, but one can show that with this a little bit complicated relations and also co-product, this algebra, the byproduct is isomorphic to the quotient of CKSL3. So by quotienting, I mean like you have the matrix of CKSL3, you cut the lower diagonal.
The usual projection.
Yeah. So that's the quotient of CKSL2, and it's isomorphic as half algebra actually. So and then we call it CQP, where P is maximal probability subgroup of SL3. So that's quite nice, even though the relation is a little bit uglier, but yeah, the isomorphism is quite nice. And now we want to construct differentials on CQP. Probably this is the new calculation that maybe, I don't know if it's mentioned, well, I mean, this is the new result in the paper. So yeah, I just recall again A and B. And again, similar to previous construction, to construct the differential of the byproduct, we only need the data we need is just differential of the quantum plane, differential of B, and then we will find the differential of A later. Okay, but here the differential of quantum plane is given by this. So the bimodal relation is given by, well, there are four relations. Yeah, 4 relations and the coproduct as well. And yeah, as I said, we want to find the differential on CKGL2 because CKGL2 has lots of differential. There are 3D calculus and there are 4D calculus, and we will show that in by requiring B, we will get the 4D calculus of omega 1A just by requiring this omega 1B. Of course, we extend the coaction differentiably. That's just the requirement. And this is the proposition. So the 4D calculus of omega CQGL2 is strongly backovariant external algebra, such as these 2 conditions is hold. So yeah, the coaction of CKGL2 on the quantum plane is differentiable, and the determinant of inclusion is also differentiable. It means that this is extend to the differential of CKGL1 becomes the sub differential on the differential of CKGL2. That's what we have. And here for 4D calculus, I don't write what is the full structure of 4D calculus, but just write some. So we have dA times A, dB times A, and until D times D and so on. So there is like 16 relations there. But I don't write everything because it's quite ugly. Yeah, that's probably the problem with works on computational. So you got some results, but it's just not looking nice. But at least we can get everything. But here, how we got it, I didn't. So what is delta R to be differentiable means? So if this is our actions, so if this is our action, let's say delta Rx is X tensor A plus Y tensor C, what is the coaction of delta? Sorry, what is the coaction of dx? The coaction of dx, we just applying the Leibniz rule. So we have dx tensor A plus dy tensor C plus X tensor dA plus Y tensor dC. So basically, it's the same process as previous example. And then let's say we have one relation. Let's say we have dx times x equal q square x dx. We compute that, and then we compare we compare the resulting calculation, and then we will find some structures to be. We don't find all structures. We don't find all relation in for the calculus of CKGL2, but just a bunch of them, not all. And that's because here, let's say we want what is the AA, what is the AB, and so on. We have 16 unknowns relation that we want to find, but the relation that we have is only like here 4. So it's really not really enough to obtain all relation, because we have more unknowns than the, I don't know what's the English, just the known equations. So we have more unknowns than the equations. So that's why it's not enough in this case by requiring differentiable coefficients. But anyway, in particular, relations involving DAD, DDA, DBC, and DCB, it's not obtained. What I mean is, like DAD, like this relation, like DDA, it's if we can see here, like in the left hand side, we have like DD is on the A is on the right, like this is like right action, and everything here is like left action. Everything is left action, so that's the relation. It's actually just by requiring differentiable coefficient, we don't get this. We don't get we don't get this. But what we get is relations between DDA and maybe with DAD. Just let's say DDA plus DAD equals something. So that's identity that we got, and this identity is still obeying Leibniz rule, but it's just not how to say, it's not, I don't know, I forgot my English, sorry, but it's not just not everything to become left action on the other sides. So that's really not enough, and this is actually happen as well in the algebra level. So this is the phenomenon is not really new, to be honest, because let's say in the construction of CKGL2 by Manin, we know CKGL2 acts on quantum plane, right? But let's say we don't know what is the relation of CKGL2 yet. Let's say we don't know that, and then to find the relation, to find this relation, what Manin does, what Manin did is we have this relation on quantum plane, yx is equal qxy, just applying coefficient there, compute, and then compare, and we only get half of the relation here. Like we don't get this relation, we don't get this relation, like dB and QBD, we don't get it, just half of relation. It means that what we got by applying coproduct on yx equal kxy is more universal or more general structure than quantum GL2. And the similar case happened in this case in differential stuff. So by just applying just by applying coactions on the differential of omega 1b, it's not enough to get differential of omega 1a. And that's why we need the second conditions here. So the rest of relations is obtained by assuming that we have also we assume this. It's not, we don't apply, this is already in this is the sub DGA of omega 1a, so just quotienting by it, and then we got the whole relations. So that's for the action and for the omega 1a. Probably that's probably the most complicated stuff here. Again, the action now after we finish with the coaction, the differentiable action, again it's more brute force, but I will give the more general formula later, but yeah, after this example. But this is, we have all the actions, and with the previous coaction and these actions, we got that the TGA of quantum plane is basically superior to the default module over calculus of CKGL2, that of the 4D calculus. So yeah, because then we get superior to the default module, then we got the calculus, and then again the calculus looks ugly, but again, but this is the calculus of CQP. And yeah, that's probably the new results, a little bit complicated, but yeah. You can probably have, there's a questions or, yeah, no? Okay, so I promise you that there is a general more construction for the differentiable actions. In this case, this is the general result is for the family of quantum plane and
Constructed. No, this will have non-classical dimension because you're taking the 4, or will it have classical? What?
so sorry, what?
How does the dimension of the calculus you've constructed relate to the classical case?
This is so GL2 has 4 dimension, and yeah, this becomes 6-dimensional. Like
and the parabolic is got.
So it has like classical should be like you quotient the lower half. So how do you have like 6 as well?
You're taking a quotient of SL3.
Yeah. 6 as well. Yeah.
1, 2, 3, 4,
6.
It should 5.
No, it's sorry.
It should have 5 dimension. It should be 5-dimensional, no?
But it's you have SL3. You have 3 by 3 matrix. You have the diagonal, so that's 3, and then
That's true.
it's 2.
Because you got the determinant.
So
You think about it in the algebra, you have the straight string matrices. So you're going to have 1 dimension.
yeah, but it's not. This calculus is not necessarily like, I think I need to remember. I need to recall it probably wrong, but the dimension not necessarily equal to the classical one.
It's not.
Not necessarily. I mean, it's general. It's like, I think like for yeah, it's not necessarily like if it's
Because once you start to work with the calculus and GL2, of course, you're back to the usual problem of the covariant calculus and SU2. And the extra dimension that's inside, okay, it's classical and GL2, but the problem is hidden inside there, so it should.
Yeah.
So okay, it makes sense that it's 1 dimension.
Yeah.
Okay.
So basically, even for quantum SU2, there's no calculus of classical dimension.
Yeah, that's what. Yeah.
Covariant. Do you want to speak covariant? If we wanted to have a left
And a right coaction, then you get this extra dimension. The smallest one is of 4 dimensions. And this is the big problem. Basically, when you work with quantum groups, differential Jimbo in general, you'll have an incorrect dimension. People still don't know how to resolve this. And that's why flags, though, when you quotient out the torus, everything works and all of these problems disappear. So the going from the flags up to the group is the big problem. And so, of course, when anybody produces a new calculus, the question you immediately ask is this resolving the dimension problem that's there?
That's the thing that I forgot before. Like the dimension of CQSL, calculus of CQSL is higher. So I guess it's clear maybe for So this is just some more general stuff. So more general construction, like so before we work on the family of quantum groups, quantum planes. So now we can generalize that stuff. So now our B is a family of quantum plane VR. So B is a algebra generated by, this is kind of row vector, and then it has some relation here. So the ball x1 is like x tensor identity, and it has this relation where R is the R matrix satisfying quantum Yang-Baxter equations, and our A here will be the FRT algebra. So this FRT algebra is the matrix algebra generated by, well, like kind of matrix like T satisfying the RT1, T2, RTT relation. RTT is equal to TR. But this is FRT. This is just still by algebra, not half algebra yet. But again, for the coaction and for the coactions, we don't really need the half algebra. We will need the half algebra later, but before we can just work on by algebra. And so here we have the coaction of AR on VR, just simple X tensor P, and its differentiables. And then now this is the general formula for the differentiable action on the family of quantum plane. To compute this, to be honest, there is to find this, there is no like maybe categorical construction and so on. But this is obtained by reverse engineering. So like we want the delta R and the action satisfies the other different module. So if we assume that, and then we can find just by simple observation we can just find this, to be honest. So that's why I say that the differentiable action in general case, like in any algebra, X on any braid half algebra, it's probably more complicated than that. But yeah, at the moment for the family of quantum plane and family of FRT algebra, we have these nice actions. And with this coaction and these actions, this is not yet enough to be so VR is yet a different module over A, but our A is not FRT algebra. Our A here is FRT algebra, but because it's just by algebra, how we make it to be half algebra? It just we take the adjoint. So we adjoin the element D inverse, where D is the quantum determinant, which is the group-like elements and central in AR. So that's we adjoin, and we have the inverse, and also with differential of the inverse, it's easily computed. And then VR becomes the different module over A. And then again, this is just the differential structures and the algebra structures, and also the coactions. So the previous examples that I talked about 20 minutes is actually the special case of this. Let's say for GL2 case, if I take R to be the R matrix of GL2, then we will get the previous examples. So that's probably it for the results. Maybe if I have do I have some time, or yeah, okay. So this is, I just want to talk about what's after this calculation is finished, what's next. So probably what I'm thinking, I don't know if it will work or not. It's just some idea, but so there is a construction called double byproduct. So not just byproduct, but double byproduct. So again, we still start with yet another module over A. But now we have this another yet another module. Sorry, another braided half algebra in sorry. We have, sorry, maybe I need to. So again, we start from the byproduct, the previous byproduct, but then we have another byproduct. So here another byproduct is C bar. I don't know how to call it, like C bar and A cross A. Where C and B here is a braided pair, like braided dually pair, and C bar it's basically like C but with some braided opposite product. Yeah. So there is a pairing between, so there is a pairing from C tensor B to the unit of the modular category.
As a dual somehow in the category of Drinford A modules?
Yeah.
Okay.
Like it's like pairing in. Yeah, the differential calculus, yeah. So we have a double byproduct. This is, I think, I don't know first time considered by who, but I first read it in Sean's paper. We have a because this the byproduct of A and B and byproduct of C and A is they are not really dual to each other. I mean, they are related, but not dual to each other. So we can glue them together. So we have a double byproduct here. And in the case of B to be finite dimensional, if you know, and A is to be co-quasi-triangular half algebra, if you know what does it means, D also becomes co-quasi-triangular half algebra, and it's called co-double bosonizations by me and Sean. The question is similar: can we construct the differential on D to be the double byproduct of differentials? And in particular, if C is not just the braided dual, but also a dual as a vector space, it's maybe it will give something. This is because in my last paper, it's a special case. We consider C to be not just dual in model category, but also as a vector space. But it's just a special case, but yeah. So probably some talk if this is to be if C bar to be the star, then probably we will need to define this. But generally, if we have a half algebra and the dual, probably in general we don't have these differentials. What we have is probably the co-differentials, right? So that's why maybe in this case we need TGA and also differential graded coalgebra, and maybe everything is finite in n forms. Just some talk, but and then if of course this is some it's still in progress, but yeah, it's not done yet. Just maybe it's wrong, maybe no, I don't know, but yeah. But motivated example is it's also not computed, but let's see if I can say something. So let's say Q to be n of unity, because here I want to work on the dual. So to be safe, I want my everything to be finite dimensionals. So assuming we have Q to be n root of unity, now I want everything to be finite dimensional. So I want reduced quantum torus. So the torus is quotient by Tn minus 1, and the quantum length is also reduced. So we have x to the power of n is 0. And in this case, for the quantum line, the dual will be quantum line again, because it's just one dimensional. But I also want it to be reduced. So then this is already computed. This is true in algebra level. So D is of algebra. The byproduct of algebra generated by x dy. The relation is simple. So this is the x. This relation is the cross relation. Looks very simple. Coproducts is nightmare because it depends on n and it's a summation. So it's nightmare. Looks horrible. The nice thing about the byproduct here is this is actually isomorphic to the reduced quantum SL2, but only if n is odd. If n is even, it's not isomorphic. The isomorphism is given like this, and yeah. So that's the byproduct. The byproduct says, and the question is, the first question is not related to differential stuff as well, but because I mentioned that because n is odd, then D is isomorphic to reduced quantum SL2, and we and D from the theory, D is a co-quasi-triangular half algebra. Then at n odd, the reduced quantum SL2 is co-quasi-triangular. But for n even, we don't know if it's co-quasi-triangular or not. And similar problem actually happened in the dual version. So I talked with Sean before, and basically people assume everything to be co-quasi-triangular or quasi-triangular, even in if n is even, but with people assume that, but just because the general stuff, the non-reduced stuff is quasi-triangular or quasi-triangular, but apparently for n even, to be honest, we don't know. And again, what calculus that if we can construct the double byproduct of the calculus, what calculus we find on the reduced one? I guess it will be 3D calculus because it's generated by, this is one dimensional. So probably will be 3D calculus of CKSL2, but to be honest, I don't know. But just probably some questions that I have in mind. And the other stuff is probably more physics. So basically, I want to, well, we have a quantum space-time acting or coacting on the quantum Poincare groups. Here, quantum Poincare groups is basically a family of whether double cross product or cross product of the of CQSU2 or UKSU2. Basically, we want to classify a quantum or Wigner-Little's group in the quantum Poincare groups. And what is Wigner-Little groups? Is this? It is the irreducible co-representation of the quantum Poincare groups, such that the mass agent value is either finite or zero. It's physics stuff, and to construct that, this is the agent value of the mass agent value is coming from the wave equations, and wave equations to construct that we will need differentials on the quantum Poincare groups. And the thing is, because this is quantum Poincare groups are given by the family of double cross product or cross products, and yeah, their calculus could be constructed by the method that I presented before. So that's another problem. This is proposed by Sean, and yeah, should look at it, but yeah, maybe later. So yeah, I guess that's it. So the talk mostly from the reference 1, but the stuff about double byproduct is from reference 2, and also it's mostly I take more material also from Beck's and Sean's book, and also Sean's and paper by Sean's and Tao, and also Ronowitz. So I think, thank you.
Questions from the audience or online? If anyone wants to raise their hand. Freddie, no, he's clapping, not raising his hands. Okay, well, if they don't, then I have a question. I mean, to go back, so when you're talking about this double bosonization or double co-bosonization, you assumed it's finite dimensional.
Yeah.
I mean, what about the extension to the infinite dimensional case?
I don't consider it in my work before. The thing is, it's not necessarily can be done because when we construct this, when we construct the double co-bosonization, sorry, the co-double bosonization, I took the original double bosonization by Sean and dualized it, and it happens that it doesn't work in at my work. It happens that it doesn't work in infinite dimensional. Maybe there is a way to make it work in infinite dimensionals. I just don't know. But if you think again, like if you have algebra, if the algebra is not finite dimensional, it's not necessary. You don't really have co-algebra. I think maybe I interchange it, but yeah.
Okay. I mean, I'm interested. I was given this problem, but
Yeah.
Rita, please go ahead. Rita, yeah, if you have a question, please go ahead.
I cannot hear.
Hello, Rita.
Yes.
Yeah, if you have a question, please go ahead.
Yes, I do have a question. So first of all, thank you. Very exciting talk. And I'm also very interested in
Thank
the
you very much.
Poincaré. You see the differential calculus and also, so I am sorry, but for like 5 minutes, I had the difficulty hearing. So did you
Yeah.
say something about the braiding inducing the calculus? Did you say something? You have the action on the plane, and then on this semi-direct product quantization, you induce the calculus via it. Did you say something like that?
So, sorry, can you repeat again?
So at some point you were showing a slide. I had a hard time listening because there was a problem with the audio for like 5 minutes. And when at some point you were saying that in analogy with Manning, that induces the deformation
Yeah,
of
yeah.
the plane to the GL2Q, you were
Yeah.
saying something inducing the differential calculus. Am I right? Because I think this is what happens. And also Majid was having that's right. Yes. Can you say more about that?
Yeah, yeah. So like for Manin,
Yes.
maybe for Manin constructed CQGL2.
Yes, of course.
And his construction is by so you have the relation on quantum plane, so y-axis is equal qxy,
Yes,
and then we take the coaction, but
Yes.
this coaction does not give the full relation of CQGL2.
Sure. Yes.
The similar thing happens in the differential. So if I have quantum plane and it's differential, I think, yeah, this is the differential of quantum plane. I apply the coaction on this differential structure, I will get some bimodal relation on the differential of CQGL2.
Sure.
Only some. So it's similar to Manin.
But
And to have the
Yes.
and to have the full structure of the to complete the structure, I assuming that the differential of CQGL. Sorry, I'm assuming the differential of CQGL1, where CQGL1 here is similar like quantum torus. I think it's here. Yeah. So I'm assuming d times d equal q squared.
No, I understand that because since you mentioned Majid, he has that the braiding will induce a calculus on that, right? So you have a braiding on your algebra will also induce, and that I was wondering what was the relation, but you have not probably looked into it, right?
Yeah, probably not, but
Okay.
yeah.
I see. Sorry. Thank you very much. It was very nice. I really
Thank you
liked
very
it.
much.
Thank you.
Very much.
In the audience or from online? No, doesn't appear to be the case. Then we thank Ryan again.
Thank you very much.
So next week's talk is by our own Arnab Bhattacharjee, who will speak here in person.
So
Arnab, you can maybe give us the title.
I should close it or?
So the title of the talk is basically the weak expectation property of discrete quantum group algebras.